sesi riset arkeologi bahasa dan sastra, yang saya hormati Bapak Sofwan Nurwidi selaku Kepala Pusat Riset Arkeometri, serta teman-teman peneliti dari BRIN sekalian. Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi, salam sejahtera untuk kita semua. Izin memperkenalkan diri, saya Niko. Pada hari ini saya akan bertindak selaku moderator dalam kegiatan sharing session kita yang bertajuk Cosmogenic Burial and Luminescence Dating Method for Quaternary Prehistory. Pada sharing session pagi ini kita sudah kedatangan 2 orang presenter yang nanti akan masing-masing dari mereka akan mempresentasikan paparannya. Lalu pada awal kegiatan ini nanti akan dibuka oleh Pak Heri Yoga Suara, ditutup oleh di akhir presentasi dan sesi tanya jawab nanti akan ditutup oleh Bapak Sofwan Nurwidi. Mungkin untuk mempersingkat waktu kami berikan pada Bapak Heri. Pada Bapak Heri kami persilakan untuk membuka acara ini.
Apakah suara saya terdengar?
Terdengar, Pak.
Baik. Baik. Terima kasih kepada pewara. Assalamualaikum warahmatullahi wabarakatuh. Salam sejahtera untuk kita semua. Shalom, swastiastu, namo buddhaya. Salam kebajikan dan rahayu. Yang saya hormati Pak Sofwan sebagai Kepala Pusat Riset Arkeometri, para Kepala Pusat Riset lainnya yang ada di webinar ini, para peneliti senior di kalangan arkeologi, dan juga teman-teman yang hadir di dalam webinar ini. Selamat pagi and very good morning for Dr. Tuha and Dr. Mahmud Abbas. Sorry, I will speak in Bahasa Indonesia for this introduction. Pertama-tama saya mengucapkan apresiasi kepada Pusat Riset Arkeometri yang pada hari ini membuat kegiatan sharing session berjudul Cosmogenic Burial and Luminescene Dating Method for Quarterly Prehistory. Saya kira sharing session ini menjadi sangat penting karena seperti yang saya baca di dalam ringkasan acara ini, bahwa di dalam riset-riset arkeologi, khususnya arkeometri, pertanggalan itu menjadi hal yang sangat penting, karena pertanggalan inilah yang kemudian bisa menguak tentang usia dari artefak, dari situs, dan lain sebagainya, sehingga diperlukan metode-metode yang terus-menerus diperbarui. Dan kali ini, karena sifatnya sharing session yang dibawakan oleh Dr. Tu Hua from Santo University and Dr. Mahmud Abbas from Jiaing University, ini akan menjadi hal yang saya kira sharing session yang sangat penting. Yeah, actually I met two of you in Sangiran a week ago, and I heard also about some conversation about your research in Indonesia. And of course, this is very important for us because BRIN trying to have effort to have like IMS and etc. and to strengthening our laboratorium related with archaeology and related science using this dating method, ya. Nah, jadi seperti kita ketahui, BRIN sedang berusaha untuk melengkapi berbagai laboratorium yang dapat digunakan nantinya untuk kegiatan riset arkeologi maupun riset-riset lain yang mempergunakan uh, metode pertanggalan sebagai salah satu hal yang penting di dalam riset-riset yang ada di arkeologi maupun di ilmu lainnya. Dan sangat beruntung kita kedatangan dua orang tamu, Dr. Tuhua dan Dr. Mahmud Abbas, yang saya kira punya pengalaman yang cukup banyak ya berkaitan dengan pertanggalan yang dilakukan. Ya, kebetulan saya bertemu dengan mereka minggu lalu di uh, Sangiran dan juga saya mendengar berbagai konversasi terkait dengan kegiatan-kegiatan riset yang dapat dilakukan. Saya kira karena kegiatan sharing ini adalah sharing yang relatif cukup langka juga dan juga ini sebagai persiapan kita untuk berbagai kegiatan riset arkeologi yang lebih bersifat kolaboratif. Jadi diharapkan para peserta webinar ini tidak saja dapat mengikuti dengan baik kegiatan webinar, tetapi juga bisa menjadikan ini sebagai platform kolaborasi untuk riset-riset terkait arkeologi, khususnya yang menggunakan berbagai peralatan laboratorium. Saya kira itu yang bisa saya sampaikan di dalam kesempatan ini. Oleh karena itu, dengan memohon rahmat yang kuasa, webinar berjudul Cosmogenic, Burial, and Luminescene, Dating Method for Quaternary Prehistory secara resmi dibuka. Assalamualaikum warahmatullahi wabarakatuh. Om Santi Santi Om. Rahayu, Rahayu, Rahayu untuk kita semua. Terima kasih.
Waalaikumsalam warahmatullahi wabarakatuh. Terima kasih Pak Heri telah berkenan untuk membuka acara ini. Untuk selanjutnya saya izin untuk eh, mengantarkan sharing session pada hari ini dengan bahasa Inggris dan bahasa Indonesia. Jadi supaya lebih nyaman juga untuk speaker kita, dua speaker kita. Dan untuk menghormati dua speaker kita, saya izin mengulang untuk mengintroduksi kembali acara ini dalam bahasa Inggris. So, good morning, everyone. Today, we are going to have a sharing session from Research Center for Archaeometry with the theme of Cosmogenic, Nuclide Burial, and Luminescence Dating Method for Quaternary Prehistory. My name is Nico. I will be the moderator for this sharing session. And today we have two gentlemen here in our office. Good morning, Dr. Hua. Morning, Dr. Abbas. So Dr. Hua will deliver his presentation first, and Dr. Abbas will follow after. And the question and answer session will, for both speaker, will be held in the end of Dr. Abbas' presentation. So please, for everyone here who has a question, please take a note for your question and do not hesitate to ask in Bahasa Indonesia. I will try to translate it to English with all my limitation in English, of course. And yeah, for first of all, I would like to share to you a brief introduction for Dr. Hua. Dr. Hua is a lecturer from Institute of Marine Science, Shantou University, China. Dr. Hua research focuses on the chronologically study of late Cenozoic sediments using multiple dating methods, including cosmogenic nuclides, luminescence, and U-series dating technique related to scientific issues, including the timing and pattern of early human dispersal in mainland East Asia and peninsular Southeast Asia, evolution of marginal seas in East Asia during the Pleistocene, and evolution of large rivers in East Asia during the Quaternary. Yeah, so please everyone, please welcome Dr. Hua.
Okay, how do you share this? Sorry. Click here and share. Yeah. Okay, but can you zoom it out? Okay. Good morning, everyone. I'm Hoa, and in Indonesia, I was always known as Bobby because I don't know why so far. And Professor Widianto and all the friends in Indonesia call me Bobby here. Even my wife don't know my name, Bobby. Uh, but I like Indonesia, so I've told that the audience here are with a background of physics and chemistry, about something like that. So more about archaeology. So I will discuss about some a part of the physical uh, principle of the dating method. So if you think it's too boring, then we can, we can change the topic to the to the archaeology a little bit. So my topic is on about the cosmogenic nuclide value dating, and the theory and some recent progresses and the applications. As I've read in a paper about this sentence that the time has always been recognized as a key variable in earth science because the chronology always the basic thing we want to know when we study whatever you are about archaeology or geology or geomorphology, right? So this is why dating is very important. And sorry, we can go this. So this, okay. So this slide shows the some very routine dating methods in Quaternary. As we know that the carbon-14 only works in about 50,000 years. And Eutherius works in like 500, 600,000 years. And luminescence dating maybe 3 or 4,000 years. And above these dating methods, maybe you can have the argon in here in Sangilan because you have a lot of tufa. But the dating of tooth has a problem is that they can be reworked. So this is a problem of the Sangilan, the age of Sangilan, because someone proposed very old ages, but then we realized maybe the tooth has been reworked. So, and also, but in China, it's different. In China, we have no volcanic activities in China during the Quaternary. So we cannot use argon in China. So what we can do is we cannot rely on ESR or fission check because fission check has very large uncertainty in Quaternary. And the ESR, it works in many cases, but sometimes you have a large uncertainty. So as you can see, in this case, basically you have no suitable method for the ages which is younger than like 500,000 years. So this is why the method of aluminum 26 and beryllium 10 burial dating is very important because this method can date from 0.3 million to 5 million years, so covers most of the periods of Quaternary. And when we are talking about the cosmogenic nuclides, this kind of nuclides is produced by the cosmic rays. So on the Earth, we have the primary cosmic ray from the galaxy or from outside the galaxy, which is consistent with photon, neutron, and proton. But as we know, we have the magnetic field, so proton cannot arrive on the Earth's surface. But so we have the proton and neutron. No, we have neutron and some muon. So neutron arrived at the atmospheric and it will react with the carbon 14, with the oxygen and nitrogen and produce a series of new isotopes, such as the beryllium 10 and radiocarbon with carbon 14, right? We know which we are very familiar with. And these isotopes produced in the air or in the high high level elevation, and it's called the meteoritic cosmogenic nuclides. And it's also produced a secondary cosmic ray, which can reach the Earth's surface and react with the rocks, the minerals. And this can produce beryllium 10 and aluminum 26 inside the minerals. So the cosmogenic nuclides, what we are talking about could be related to the referred as radiocarbon, carbon-14, aluminum-26, beryllium-10, coralline-36, and neon-21. But what we are used mostly is the aluminum-26 and beryllium-10. And beryllium-10 is an isotope with poison, with a little bit poison, and most of its isotopes are stable. And what we use the beryllium-10 is radioactive. And aluminum is what we are very, very familiar in the constructions also in our life uses. But the most abundant isotope is aluminum-27. And aluminum-26 is also radioactive. And the production of this aluminum-26 and beryllium-10 can be two mechanisms. The first is by respiration by the neutrons, meaning the neutron hit the silicon-28 or oxygen-16, and will produce the aluminum-26 and beryllium-10. Another mechanism is by the muon capture. So it also can be produced from silicon and oxygen. So the what we usually use is the radioactive cosmogenic nuclides produced near the surface from different kinds of minerals, mostly quartz. And this method was proposed in 1985 by Lyer from University of California, San Diego. And he proposed the ideal model of this, that we can use these two isotopes to date the sediment of burial. And then Daryl Granger from the Purdue University, United States, he established the first chemical and physical procedures, and he was the first one to success dating the cave sediments in United States. And we have collaborated with Daryl for about more than 10 years. So they have the best lab in the world. And this method was first used to date the tektite in the desert, to date the time of exposure in the desert. And so we will skip this. But for burial dating, we can see this cartoon as a model of the method. So at the beginning, you have some. Sorry, I cannot give the laser. Yes. Okay, so you can imagine that in a rocky area, in the south area, you have the mineral but deeply buried inside the rock. So when you have a cosmic ray to come down, and you have the cosmic ray was shielded by the thickness of the rocks, so there's no cosmogenic nuclides produced inside the mineral. And then with the erosion of the rocks, the mineral become near the surface, and then it can react with the cosmogenic nuclides, cosmic rays. And after that, it continues through erosion, removed the mineral from the rock surface. So it will be transported by wind or by river and into a depositional center or like a lake or the river terraces or marine or sea. And then it will be buried by continuously sedimentation. So which will stop the cosmic ray to react with the mineral. So the production of the mineral of the isotope stopped, and then it starts to decay. So we can establish the ideal model from the exposure to burial processes. And we can imagine that when it was covered by deep thickness of the rocks, there's no cosmic ray. And then it was exposed to cosmic ray for a period of time, and then transported to the another places around the surface of the Earth, and then deposited in somewhere. So, and which is buried. So in this case, we can establish the concentration of nuclides of these 4 stages, which is at the beginning you have nothing produced, and then you have a production of the nuclides, and continuous production during the transportation. So there's a delay of that. Okay. And then after burial, the nuclide started to decay. And there's an interesting mechanism is that when the aluminum-26 and beryllium-10 is produced, the ratio of these two production rate is about 6.8. It's a constant.
I think it's mute. No sound.
Still muted. Please unmute. Unmute.
Unmute. No sound. Ruby, please.
So you can know the time of the burial, which is the time of the decay, right? And so as we are, do I need to stop? Okay. So because we are using these two isotopes, the best material for dating is quartz, because in quartz you have the silicon 28 and oxygen 26, which is the parent isotope for aluminum 26 and beryllium 10. And also quartz is very simple. You just have silicon and oxygen without any other material, other elements. And also they are very strong. They are weather resistant. So even after several million years, the quartz is still not weathered, and it still keep a closed system for the isotopes. So it's an ideal material for burial dating. And more importantly, you can find quartz everywhere. So you don't need to worry about the dating materials. So this is why quartz is widely used for cosmogenic nuclide dating. And this method can be used to date burial event from 0.3 million years to 5 million years. And this boundary was constrained by the precision of accelerator mass spectrometer, and also by the limit of detection of this machine. So beyond this lower than this age, you cannot identify. And if it's older, that's the nuclide will almost died. So you cannot find it, you cannot detect it, measure it. And the chemical method of this, chemical procedure of this method can be departed in the 4 steps. First, you have to extract the quartz with very pure quartz. So normally we have to shave the sediments, or if it's rock, we have to crush it. And we just use the grain size between 2.2 to 2.5 millimeters. And then we etch it with HF. Usually it takes half a month or maybe 1 month to dissolve the feldspars. And then we can use the magnetic machine to remove the magnetic minerals. And then we can use some heavy liquid and to remove some the remaining feldspar or some heavy minerals. So after these are produced, usually you have a very, very pure quartz. And if it's not pure enough, you can go back to the procedures to continue of purification. And after that, we can measure the quartz by ICP-OES to detect how many aluminum inside. If it's less than 100 ppm, meaning that the quartz is pure enough for the further steps. And if it's not, we can go back to do it again. So after that, we etch it in the ultrasonic base with the HF, and it can be considered as very, very pure. And for the chemical purification, we have to dissolve all the quartz in concentrated HF, which is very dangerous acid. And then we evaporate in the small beakers made of platinum, and we removed the iron and titanium by precipitation, and then we extract the aluminum and beryllium by cold precipitation, and then we clean it in column in rinse columns, and after that it can be oxided to like aluminum oxidation and beryllium oxidation, and then prepared for MS measurement. So usually this experiment takes 1 week. And we measure the samples with the AMS. We use the AMS at Purdue University because they have a very high energy, which is 8 megavolta, and they have installed a gas field magnet, so they have the best precision of the for aluminum 26. So normally when we submit paper to peer review journals, nobody questioned about our data because we use the best machine and we collaborate the best scientists in this field. And besides this, we also have this machine in China, but the energy is relatively low. It's just 3 million megavolta, 3 megavolta. So sometimes you can use it for barrier dating, but sometimes you cannot because the energy is not high enough. And also we have it in Australia, in Einstein. They have the machine of 6 megavolta, and it's also for not only for aluminum 26 and beryllium 10 measurement. It's also for some physical experiments. And also in France, in Marseille, they have a small machine of 3 megavolta, and also in British like Glasgow, they have the same machine. So, and in China, recently we have built a lot of small accelerators, but most of them are less than 3 megavolta. There was one built in Beijing, maybe a 2. Maybe they will reach 6 megavolta, but it's still under construction. So we will see if how it works in the following years. But mostly those small accelerators like 1 megavolta or 0.2, 0.2 or 0.5 megavolta, they are most useful for radiocarbon dating. They cannot be used for cosmogenic nuclides, so which is a pity. And so we're back to the dating method. I will give some to the last part of the theoretic part, and then give you some cases. So there's 2 major presumptions about this dating method, which we can use to evaluate the reliability of the dating results. First is called the steady state erosion model. To simplify things, that we assume that the samples were eroded from the source area and transported directly to the sink, which is a depositional per area. And this process has only happened once in the past 10 million years. If you have a trap or a basin in the middle and the sediment was trapped somewhere for a long period of time, and then the sediment worked out of the trap and out of the basin, and you will get the age as overestimated, which means the age is too old to be reliable, right? And another one is the sample has been buried deep enough. Normally we ask for samples buried more than 10 meters, and this is the thickness required to share the cosmic rays. So if the depth is not enough, this means the cosmic nuclides can continuously produce inside the samples, and this will lead underestimation of the ages. So these two presumptions, we have to make sure your samples are fit all of the presumptions in order to obtain reliable ages. Okay, so if the samples are satisfied with the 2 assumptions, we call it the simple barrier dating method. For a simple derivative method, this was first used in China to the Zhoukoudian locality 1, named the Snowland and the Peking Man. The Peking Man, the age of the Peking Man has been debated for several decades in China, and we use different methods to date this site. For instance, we use the uranium series dating of the fossils, and they give the ages of 200 or 300 million thousand years. And someone used the fission track, and they get the age of 300,000. And by ESR, you have 300 to 550,000. And by paramagnetism, you have the BM boundary, which is 0.7 million years, 0.78 million years. And so for a very long period, the Peking Man was cited as 300,000 or 400,000 years old. And after in the last decades, Professor Chen Guanjun used the uranium thorium of the calcite, and he got different ages. He found that the sediments in the cave should be at least 400,000 years, meaning that the uranium thorium dating of the fossils were too young. And then in the middle part of the sediments, it was dated to older than 600,000. But how much, older by how much, we don't know. So they used the cosmogenic barrier dating to date 6 sediment samples from the cave and 4 artifacts from the cave. And as you can see here, the age was not, because the age was obtained that more than 10 years ago, 15 years ago. So the precision was not so good. And they also find that some of the sediments are reworked. So they are much older than the other sediments. For instance, this one has been dated to 2.7 million years. And the others are generally the same, but the age range is big, is large. And for the artifacts, there's artifacts which is obviously very old, which is 1.66 million years old, so much older than the others. So after exclude those samples with reworked materials or with bad precision, and the rest the data give a weighted mean of 0.78 plus minus 0.08 million years old. So this age is consistent with the age of the uranium thorium of calcite and the paramagnetism. So this age has been published in Nature in 2009. And then another case is what we did in 5 years ago in Shandong, northern China. This is a small cave named the Yiyuan Cave, Yiyuan Hominin Cave, and they find a skull cap and 7 teeth from the cave. It's a very small cave. Most of the cave wall has been destroyed during the road construction, and there's also debated about the age of the cave, because the fossils were assigned by Homo erectus by the paleontologists, and the age was debated because based on by stratigraphy, it's considered as a middle Pleistocene, but according to the morphology, it could be close to Zhoukoudian or Hexian site. Zhoukoudian was 0.78 as we discussed before, and Hexian is like 0.4 million years old. So we don't know exactly what the site is. And a colleague from Yunnan University, they dated this by ESR dating, ESR series dating, and he got the age of 0.3 to 0.4 million years old. And we want to date the site, so we take samples from the layer where the fossils will come from. And we take 2 samples. And then we also take another sample from the modern river outside the cave. So we want to know whether the sediment has been buried or not before it's washed into the cave. So we can get some information from the modern sediment of the cave. So here's the result. Here, okay. So first, we analyze the morphology of this area. We can see that the rock area in this granite area, the granite area is quite different. The north part is granite and the south part is limestone. as we use the quartz for dating, so obviously the quartz should come from the granite, because there's no quartz in the limestone in this region. And so as we can see the topography of this region, there's no sedimentary basin in between. So the sediments could be washed directly from the mountain to the cave, to a river, and then to the cave. And secondly, the samples from the modern river get an age of exactly 0. So meaning that it's another evidence supporting that the sediments come from the mountain was very directly, straightforward. So that it has been not buried in any place in the middle. And then the age of the simple burial age of the other two samples from the cave, one is 0.53 and the other 0.57. So it's consistent with the stratigraphic order. But this age is not accurate enough because the cave wall has been eroded, as we can see the shape of the cave wall. In the upper part of the cave, in the vertical direction, the thickness is about 20 meters. So it's thick enough to shield the cosmic ray. But in the horizontal direction, it's not enough. So you still have some cosmic ray come from this direction, and will produce some nuclides inside the samples, and which will lead to underestimated ages. So we use a geometric model to calculate how many nuclides were produced inside the quartz, and then we can use to calibrate the ages, the burial ages. So the ages of this cave should be 0.59 and 0.66. So the age of the age of the fossils should be 0.6 million years, and is different from the ESR ages reported previously. So this is a very simple case showing how evaluate the simple burial dating. But this is not enough, because when we do the modeling of the geometric of this cave walls, it introduced a lot of uncertainties. So this method is not accurate enough. And how we can improve the ages. As we go back to the theory of the dating method, there's the sediment has been experienced 4 stages: the burial, exposure, transportation, and the burial again, right? So in these 4 stages, the concentration of the nuclides, as we showed before, is going from 0 to accumulation to a certain concentration and then decay. But when you look at the ratio of the two nuclides, it's different, a little bit different. So the ratio at the beginning, you have no nuclide in this stage, so there's nothing. And then during the exposure and the transportation, the ratio of aluminum-26 and to beryllium-10 should be consistent with 6.9. And then its decay is with the ratio also decays around with the decay of the isotopes. And if you have the post-burial production, meaning if the sample was not buried deep enough, you will have a continuous production inside the quartz, and then the curve will be raised a little bit. So in this case, the age obtained is younger than expected. So what we can see from the formula is that if you have the formula, which RT is the ratio of aluminum-26 and beryllium-10, at the beginning, the ratio should be 6.8. And then with the decay, it will be reduced. For instance, after 1.44 million years, the ratio of aluminum-26 to beryllium-10 is reduced to half of the original value, which is 3.4, right? And then if you have the post-burial production, so we can assume that you added a little bit of the atom of aluminum-26 here and some beryllium-10 here. Then you got a ratio which is higher than 6.4, meaning the age is younger than 1.44, right? So this is why the age is younger. And then the calculated age should be 1.12, right? So this is this is underestimation. And then if you take a series of samples, like for instance, you take 10 samples from the same layer, and then originally their ratio should be the same because the age is the same, right? But the exact concentration should be different, but the ratio should be the same. And then you add the same, and then this isotope, the ratio, if you plot the concentration of their nuclides on a coordinate, and you will see they are lying on exactly in a straight line. And this straight line also cross the origin, right? This is the ideal cases of simple barrier dating. And then if these samples have the post-production rate, post-production nuclides, and meaning you add the same values to each samples, and then the ratio changed. The ratio changed. But if you plot them in the coordinates, they still lie in the same line, a straight line. Okay, it's still in a straight line, but the incept of this line is not zero anymore. It doesn't cross the origin anymore. So using this method, we can know that the post-production in the samples, it doesn't change the slope of the line. It's just change the incept of the line. So using this idea, we established a method named the isochrone dating method. The isochrone dating method is we take like 10 crust, 10 gravels from the same layer, and then we fit a line. We use their illumination 6 and barium 10 concentration, and we fit a line here. And this line, the slope of this line indicates the age of these samples. And the incept of this line indicates the post-production of these samples. So this method, using this method, we can ignore the post-barrier production and give the real age of these samples. And also, if you find some samples lie below this line, meaning that this sample has been reworked. And if it's above the line, meaning that you have made some mistakes, because theoretically, you cannot have a data above the line, right? So it indicates you have made some mistake in the laboratory work or in the field work. Maybe you take the wrong samples from different layers, right? So the advantage of this method, of the isochrone method, is that it can be used to date the samples with not deep enough buried, like 5 to 10 meters deep. And also it offers a means of internal check to exclude the reworked samples. And also it can avoid the laboratory or field work mistakes. So this method has many advantages, but there's a disadvantage, which is the prices of analysis rises by 10 times. So normally we use, for one sample, we need about $2,000. But if you use the isochrone dating, maybe you need $10,000 or $20,000 for one age. So it's very expensive method. Yeah. But even it's very expensive, but we still want to use it to date some very important archaeological sites in China, and maybe in the future we can date some site in Indonesia, like in Sangilan. And the first case is the Lantian Homo erectus site in China. This site, they found a skull cap in the 1960s in northern China. And the age has been debated because previously it was reported to be 1.2 million years, which is close to the Jaramillo event. And then another group published a new magnetostratigraphic framework, and he proposed that the age of this site should be 1.6 million years. So quite different. And what we can do is that we take a series of gravels from a layer below the artifacts, below the human fossil. As we can see, that because the samples were not buried deep enough, the simple barrier age are not reliable. For instance, although the samples were from the same layer, but the simple ages could be 1 million years, 1.2, 1.1, or even 0.7 million years. So meaning that the simple barrier age is not reliable. And so we can use the isochron. We plot all of the data in a coordinate. And we can see that clearly that all of the samples are lying in the same straight line. And the slope of this line indicates the age of this gravel layer is 1.8 million years. And 1.8 by 1.8 is consistent with the layer of RGY in RGY subchron in the magnetostratigraphy. So our age is consistent with the new paleo-magnetism study. So meaning that we support the age of 1.6 of these fossils. So this makes the Homo erectus of Lantian site the earliest in China and the second earliest in Eurasia. And then another famous case is the Stekfontein. Stekfontein is a very famous site in South Africa. And in this site, you find a different kind of humans. You have Australopithecus africanus, and you have Australopithecus promiscuus, and also Homo erectus. So different kind of hominin lived in this cave. And this is a famous skeleton named Littlefoot, the Littlefoot, and it's discovered in the 1990s. But the age of this Littlefoot has been debated. It's the Australopithecus promiscuus. And the age of Littlefoot has been debated. At the beginning, they think the fossil should be about 3 million to 3.5 million years old, based on biostratigraphy and also ESR dating. And then by paleo-magnetism, it was dated to 3.2 and 3.6. So generally, the same about it should be 3 million to 3.6 million, right? And then Daryl Granger from the Purdue University, they dated this site with cosmogenic nuclides, but he used the simple barrier dating method, and the age obtained for the Littlefoot is about 4 million years old. So they have 3 samples around the fossil and give a weighted mean age of 4.1 million years old. So this is older than the previous estimated. And this age was generally accepted because the modern samples outside the cave were dated to 0 age. And then the cave wall is very thick, it's more than 20 meters. So they think the post-barrier production should be ignored. And so this paper has been published in Science in 2003. But after that, there was a new paper published about the site. They used the uranium lead of the fault stone that covering the fossils. So the age of the fossil is the age of the fault stone was dated to 2.2 million years old. So generally, we think that the carbonate covering a fossil should be close to the age of the fossil, because you cannot have the fossil cannot be resistant for a very long time if it's not fossilized, right? So this has been challenging to the age of cosmogenic nuclides. So even Granger, he admitted that maybe the sediments dated by cosmogenic nuclides has been reworked inside the cave system. So meaning that it's not reliable. But after that, there's a new study. They studied the microstructure of the fault stone covering the fossils. And they found out that the fossils, there are a lot of natural void, natural cavity below the fossils. And the fossils were collapsed and fall apart into 2 parts during an earthquake. And after that, the fault stone grow around the fissures of the fossils. So meaning that the fossil could be much older, and then the fossil breaks. And then in about 2 million years ago, the fossil breaks, and then you have the fault stone. You have water flow around the fossil, and then you have flow stone, you have a carbonate grow around the fossil. So meaning that the uranium lead of the fossils, of the flow stones are not reliable. So to solve this problem, and Daryl made the isochron dating of this site, he collected different kind of minerals from the site, and also some manipulate of audivine of Homo erectus. So they give the age of 6.7, 3.7 million years old of the little foot. A little bit younger than previous published, but it's consistent with the biostratigraphy, and also it proved that the uranium lead dating is wrong, right? So this is the story of the stack fondant, and after that they also published another paper in. This paper was published in Nature, and then after that they published some new results about the Australopithecus in the cave to 3.4 million years in PNAS last year. So this is the stack fondant, and to summarize, so I don't have time to make a PPT about the more study of we do in China, but here's the summary that we dated many Homo erectus sites or Paleolithic sites in China, and we found that Paleolithic sites or Homo fossils dated to 1.7 or 1.6 million years from South China to Central China, even to Northern China, and we think that and the age is about the same age of the Sangilam or Mojokerto. So this means this provides a very robust chronological framework for the disposal of Homo erectus in East Asia and Southeast Asia. So if we have time, I can present the details of our work about this framework. Okay, so this is my talk today. Thank you very much.
Yeah, thank you, Dr. Bo, for your presentation, for your super presentation, I mean. So yeah, we will moving forward to Dr. Abbas' presentation. Before that, I would like to have a brief introduction also for Dr. Abbas. Dr. Abbas is a lecturer from School of Geography and Tourism, Jiayin University, China. Dr. Abbas is a geologist specializing in Quaternary geology, sedimentology, and geochronology. His main research interests are to study lakes and wetland sediments associated with prehistoric artifacts using OSL dating, optically stimulated luminescence, to investigate the connection between archaeology and climate change, and to better understand pattern of hominin dispersal into Eurasia. Yeah, so everyone, please welcome Dr. Abbas.
Thank you very much for the introduction. Today, I'm going to talk briefly about the principles of luminescence dating method, and then I will move to talk something about my research area and our previous or recent publication. So I will not go in depth with the luminescence dating. I will just talk a little bit about what is luminescence dating and how we can collect samples from the field and in the lab, what we are doing, and why this method is reliable recently. So in general, we know that there are several dating methods have been recently used, particularly to date sediments and archaeological sites from Quaternary and late Quaternary. Basically, for example, we have the radiocarbon dating method, uranium series, cosmogenic isotopes, and argon-argon, and all of these methods could be applied on specific materials. For instance, radiocarbon is an organics, the genesis, but also it has some limitations due to the contamination and reservoir ages. For the uranium thorium dating method, it needs some complex calibration, and also maybe the carbonate might have some influence from the detrital contamination or heterogeneous input. The cosmogenic isotopes, my colleague Tanpa and my friend, he just gave us some idea about it and its application. And potassium, argon could be applied on volcanic ashes. So generally, those methods could be applied on specific materials. But the luminescence dating method has been recently established, like in 1980s to 1990s, and this method can provide us some crucial information about the landscape evolution and geomorphology, ages, and provenance. And it is a small method that has made a big impact on geosciences and also in archaeology, as it could be applied on archaeological materials as well, or to date, archaeological sites to be precise. So this method is good because it directly dates the landscape features and some minerals that are naturally occurring and very abundant, like quartz and feldspars, are used for this technique. And it provide us the age of the deposition events. It's a Purial dating technique. So it tells us the time when the sediments have been deposited, okay? And it range like varies between like tens of years, hundreds of years to hundreds of thousands of years. Basically, Tuhwa said that the cosmogenic nuclide can give us ages between 400,000 years to 5 million years, right? So the reason that I'm here in Indonesia and this fieldwork is actually to date the younger sediments, which are less than 300,000 years, to the Holocene or hundreds, tens of years. This is where my field goes, or where my method can date. And also it's different from a quartz to feldspar. If we are using quartz, it's different from place to place. Again, it may give us for quartz like 150, sometimes 200,000 years of ages, might be okay, acceptable. And for feldspar, it may give us like ages up to 500, 600,000 years ago. And it is actually very useful for dating technique and terrestrial, paleoclimatological, and tectonic research, as well as archaeology. So in basics, or in principle, luminescence dating is a chronological method that has been used extensively in archaeology and earth sciences. And basically, it is based on the emission of light, which is luminescence by commonly occurring minerals such as quartz or feldspar. So it may determine either the time since the mineral grains were last exposed to a daylight. This is luminescence or optical luminescence dating, or determines minerals were last heated, which is thermoluminescence. And its precision is quite okay, accepted between 5 to 10%. So what makes this dating technique useful? It is that the sediments in general, or some minerals, are acting as a dosimetry for light or heat. When those sediments or grains are exposed to the sun, they yeah, when those grains are exposed to the sun, the energy has been stored inside the crystal lattice, and then the energy starts to store inside after the deposition. What we are doing in the lab is we trying to release the trapped electrons. So this is what we call the equivalent dose. So here in the lab, the trapped electrons can be released using the radiation. We use specific radiations in the machine, in the RESO machine in general. And this is how we mount the sediments on our desks. Like we have sediments of specific grain size. The visible ones are opaque, as we can see, but after heating, when we heat them at specific temperature during our sequence protocol, the sediments can be changed into this, and this can provide us here some crucial information about the signal, the intensity of the signal, and also the provenance of the luminescence technique. So to summarize the optical stimulating luminescence dating, here we have sediments, those sediments exposed to the sun. After a while, the energy is stored inside those sediments, and then we have a contribution from alpha, beta, and gamma, and in those sediments after a burial. So to establish the age, we is based on this formula, the burial dose or the value dose, what we measure in the lab with the annual dose rate can give us the age of luminescence dating. So the total energy accumulating during a burial, it is the burial or equivalent dose, and the energy delivered each year from the radioactive decay, alpha, beta, and gamma. This is, we call it the annual dose rate. In general, in the lab, we have some field activities we are doing, like to collect the samples. We have to be careful while collecting the samples. The samples should not expose to the sun, so we are using the luminescence tubes, or sometimes we cover ourselves with a very thick blanket. We collect samples for both things to date, the burial in the lab, and also for the dose rate measurements. So in the field, we collect the sample. This sample for the equivalent dose must be protected from the sun. And then we take it to the lab. In the lab, we start to separate the sediments to dissolve the unwanted materials, for example, the carbonate, the organic matter, and also we do the etching to get a pure quartz. This quartz will be used in the machine to date the equivalent dose, and also we collect some other samples for the dose rate. We send them to other labs to do like uranium, thorium, and potassium. And also to establish the formula, we have to consider the latitude, the longitude, and the humidity. All of these factors have a huge impact on the results that we will get from the age. This is all the dose rate. Okay. So for the sampling strategy is very important. A number of questions must be raised during sampling, like are there materials at the site suitable for luminescence dating? This is very important, like cars or feldspar. And would the luminescence age be clearly related to the archaeological sites if we are working on archaeology and archaeological sites? And also, are the samples likely to be in the age range of luminescence dating of the materials? For example, when we were in Sangiran, Tohua was collecting samples for cosmogenic nuclide from the lower layers, which are like 700, maybe 800,000 years, more than 500,000 years. And I was collecting luminescence samples we estimate that it is less than this age from the upper part of the section. So the details of this decision will vary from one site to another site, and a good sampling strategy is probably best designed in discussions between the project manager and the luminescence specialist. Here, for instance, some of samples have been collected from different sites during my work on Egypt, in Jordan, sometimes at night in Oman, as you can see here, and fluvial sediments from the central of Oman. And here we can see the luminescence tube. First, we have to clean the section to get some fresh materials. So again, as we previously said, that care should be taken to avoid exposure to any source of daylight or any light or radioactivity. The applications of luminescence dating is wide. Actually, it is the best for Julian sediments, actually. Lacustrine sediments, moraine sediments, and other archaeological applications. In general, the lab is like we call it the dark room. Only a red light can be inside the lab in the rooms. And for the value dose, we have to prepare some sequences, some aliquots, and the range of the aliquots will provide us growth curves and decay curves that based on this, we can get the DE or the equivalent dose, and then we do the calculations of the dose rates to get the final edge. So this is just a brief idea about the luminescence dating, how it works, and how we do the sampling and other things in the lab. So for me, I work, my major or my main research work is actually conducted in the Levant area in Jordan. So today I would like to share with you my recent research and how I employed luminescence dating methods to improve our ideas about the paleoclimate and human dispersals in the Levant. So I will talk about the last glacial cycle window of a human dispersal out of Africa via the Levant. And the background here is a site in the southern of Jordan, Wadi Garandal. And this work has been conducted in collaboration with Chinese scientists, Australians, and a British research group, of course, with Jordanian ones. So first, in this presentation, I will introduce or present a brief idea about modern human dispersals out of Africa. And as we suggest that the Levant and Arabia was a key route for human dispersals out of Africa, I will provide like a brief introduction about the significant findings and archaeological and climatological findings in these regions. And then I will talk about why wetland sediments contributed, or why the paleohydrological records actually and paleoclimate contributed in this dispersal event, and what is the paleoclimate implication. And then I will present some new model that we are working on right now about what has been in Arabia and in the Levant, and how the human occupation patterns during the last glaciation. And then our summary. So as far as we know that modern humans first evolved in Africa, as revealed from Jebel Arhoud in Morocco, as early as more than 300,000 years ago. And today we are everywhere in the globe. And the main question is, how did this come to happen? And when and how did Homo sapiens disperse out of Africa? What are the factors enabled this dispersal? Are the main questions we are going to discuss in this presentation. So first, as far as we know that Homo sapiens first evolved in Africa here 300,000 years ago. We got like a human skull in Jebel Arhoud in Morocco and Homo Kabish formation in Ethiopia. And then we have some key sites in the Levant, for instance, Sukal, Kafze, Mycelia. In Mycelia, they found a human skull dated to almost 200,000 years ago. And in Sukal and Kafze, they found some human fossils were dated to 130 to 90,000 years ago in Palestine, in the north of Palestine. And then we have some remarkable findings in Arabia right here. So basically, the first step out of Africa, as far as we know, is Arabia and the Levant, because it is a very important geographical position between three continents, between Africa here and Eurasia and Europe, right? I mean, Asia here and Europe. There was actually a new findings from a Greek that found some Homo sapiens with Homo neanderthals were dated to 210,000 years ago. So the story of a human dispersals or hominin dispersals out of Africa need to be further explained. So how humans have dispersed out of Africa, there are like two main corridors. The first corridor is the north route via the Sinai Peninsula, as they went from the Nile Valley to the north of Africa in Egypt here, crossing the Sinai Peninsula. And from Sinai Peninsula, they entered the Levant and then into Arabia. The second one, and this was during the interglacial periods, let's say. The second route is the southern route via the Bab el-Mandeb Strait, as we know that here, Africa and here is south of Arabia, right? And in the Gulf of Aden here, the bathymetry is very narrow, but during the glacial periods, the sea level was lowered, and maybe humans were able to cross Bab el-Mandeb Straits and there are some evidences. So this is like a big debate about the north route or the south route, but the north route has been considered as a failure dispersal before 70,000 years ago. Okay, so during the last interglaciation between 129 to 71,000 years ago, there are some evidence of dispersals into the Levant, but archaeologists and Christopher Pye in Science published a paper and he considered this dispersal as a failure. Why? Because they couldn't find any archaeological tools or evidence of a human occupation after 90,000 years ago. So they may have just dispersed or occupied for a specific time and then they cannot persist. So modern human dispersals of early Homo sapiens, modern dispersals of early Homo sapiens into the Levant possibly took place possibly as early as 180,000 years ago. And this is considered as a failure dispersal, might or likely replaced by Neanderthals, because Neanderthals were actually exist at that time in the Levant and also in Eurasia in general. The high intensity, I mean, and might have been enabled by environmental shift, but the Levant is considered as a possible contact zone between Neanderthals and modern humans. There is another coastal model or another model that talks about human dispersals out of Africa, which is during the last glaciation, actually between 60 to 50,000 years ago. This model suggests that there was a rapid coastal dispersal from Africa into Arabia and then Eurasia to the rest of the world. And this is, in this model, it has been also suggested that modern humans have had no chance to enter the terrestrial or the inland of the Levant and Arabia, because actually presently it is a harsh environment and the desert. There are no resources, so they just went through the coastal route. Okay, and this is took place during a glacial period when sea level was lowered, as we previously said. But there are like some questions have been raised about this, and now we will explain what we have in the interior of Arabia and the Levant, the findings. But before, I would like to introduce to you what is the present climate of the Levant and Arabia. So in the Levant, as you can see here, we have three major factors that bring climatic factors that bring precipitation into the area. We have the major one, the winter Mediterranean cyclones. The winter Mediterranean cyclones contribute bringing moisture and precipitation into the north of the Levant above here. And we have winter, actually only during the winter months, I should say, between, let's say, December to February or to January, something like this. Not September, actually, October or November. It starts rain in my region. And we have the winter tropical blooms, which is a France of the intertropical convergence zone and the Red Sea troughs that bring some flash flood events also during winter months in the southern part of the Levant. Summer East African monsoon may have some influence in Arabia, and the Indian summer monsoon have some influence in the south of Arabia, but they both cannot reach the Levant or our research area. Okay. In Arabia, again, it's a presently very harsh and desert environment. The mean annual precipitation in Arabia and also in the southern part of the Levant as well is very low, ranging between 50 to 100 millimeters per year. And it has like some influences inside Arabia from winter Mediterranean cyclones may reach some parts of north of Arabia, and African summer monsoon, Indian summer monsoon have some influence or bring precipitation into the southern part of Arabia. Here we can find Yemen, Oman, and also parts of United Arab Emirates. So generally speaking, our study area right now or presently is very harsh, is a desert. There is no rain, there is no water resources, not enough water resources. We are talking about the surface water resources. But actually there are some value. But is this the case in the past? Like, was the Levant and Arabia such arid environments before? Recent archaeological findings and paleoclimatic records suggest that Arabia and the Levant occupied, actually, the presently harsh and desert environment was occupied by several lakes and wetlands. And those lakes and wetlands are actually associated with prehistoric artifacts that may support the human occupation at that time. So what you can see in here, some Middle Paleolithic assemblages and rivers, like traces of rivers in the presently arid environment of Arabia, and also the dispersal routes or the potential routes for humans to disperse out of Africa. There are like three corridors. We will talk about them later on. With the presence of several lakes and wetlands in the Levant and Arabia, recent research found some significant archaeological findings. For instance, in Al-Wusta site here, a human finger pawn was associated with a lake sediments in Al-Wusta side, north of Arabia, in the Nifud desert, was dated to 85,000 ago, suggesting a human incubation at that time. And also nearby in Al-Athar Paleo Lake, nearby Al-Wusta side, they found footprints, and those footprints, modern human footprints, were dated to 115,000 years ago. So we have resources, we have archaeology. this is here we can see the finger bone, and here we can see the footprints in Al-Athar Paleo Lake. And also the research from the north of Arabia, the Nifud Desert, they found that this area have been occupied several times or subjected to several dispersal events, as we can see from the typology of the artifacts between 400,000 years to almost 55,000 years ago, as it's been revealed from Jabal Salman. So in general, I would like we talked about Arabia, we talked about the significant founding in Arabia, but how about the Levant? We want to go back to the Levant again, but I put this map to show you where is the area for the people who are not very, let's say, familiar with it. So this area, the Levant, is actually a colonial name for British. We don't like it a lot, but it is called the Fertile Crescent or Bilad al-Sham in our language, in Arabic. So this is what we prefer. So why the Levant is important in the story of the dispersal out of Africa? Again, because we have because it is the only terrestrial route for out of Africa. The other route, the south route, there is a sea, the Gulf of Aden right there. So it is the only terrestrial route, and there are human fossil records, as it is like in Sokol, Kafza, and Massilia. And also what we are focusing today is the prehistoric artifacts associated with Paleo lakes or the paleohydrological records. So we have even 3 other corridors in the Levant, the one from the Tigris and Euphrates River in the north of the Levant, Azraq Wadi Sarhan in central Jordan to north of Arabia, and the southern Jordan corridor to the north of Arabia as well. So this is, again, the Levant is the main gateway to Arabia, actually in the Southeast Asia. And no, in Southwest Asia, and no real work has been done so far in the region. Now I would like to present our results, what we have done, and what we found, and why our findings are connected with the story of human dispersals out of Africa. So here we have the wider Levant, let's say, with Arabia in this figure, and we have the suggested routes, the north one and the south route from Bab el-Mandeb Strait. And in the other figure here, we have some paleoclimatic, archaeological, and speleothem environmental records from the Levant. We have studied 3 wetland sediments are presently lying in the south desert of Jordan with the mean annual precipitation of less than 100 millimeters per year, which are Wadi Hassa here, Egregra, and Wadi Garandal. Those sites, we know that there was lakes and wetlands because it has been recorded by geologists. But those sites have been dated previously using the radiocarbon dating method, and the radiocarbon dating method revealed 20 to 40,000 years ago. So those wetlands have been formed according to radiocarbon ages between 20 to 40,000 years ago. The idea when I start working on this topic with a great input from Tuhwa actually is, as far as we have several evidence for human occupation and wetlands lakes in Arabia, why we have nothing in the Levant here, specifically in Jordan? Because if you want to cross from the Sinai Peninsula into Arabia, you have to cross Jordan, and there must be something there. So what we did is to make some integration. But to do this integration, actually, the age is the key. A real age is the key. We know that radiocarbon dating from terrestrial environments and also from the desert is challenging because in the desert, we don't have enough materials. Sometimes we cannot find the charcoal layer. It is very rare to find it. But what we have sand. What we have on the sand, we have many quartz and feldspars, you know? So we start to evaluate the previous work using the radiocarbon or by radiocarbon, and we applied the luminescence dating methods and 3 sites, here Wadi Hassa in West Central Jordan, Egregra, and along the Jordan Rift Valley, and Wadi Gharandal in the south of Jordan along the Jordan Rift Valley too. So we have investigated in Wadi Gharandal 3 sites, 3 sections, wetland sediments, GH1, GH2, and GH3. And we established a chronology based on this. In Wadi Hassa, we delineated actually the extent of the wetland at that time or during the time of its formation, and we have investigated some sites into there. We and in Wadi Gregra as well, we have established a stratigraphical, a chronological framework from our sites. And what we have found that the previous ages of uranium, of radiocarbon, which was like between 20 to 40,000 years, were not actually precise. Our new ages revealed the formation of wetland sediments in Wadi Hassa. It goes back to MIS5 between 81 plus minus 5 to 43 plus minus 3. All of these are luminescence dating, luminescence aging, dating, or dates, or asal dates, sorry, luminescence ages. And in Wadi Egregra, the maximum age or the one set of the wetland sediments was between 86,000 years ago to 45,000 years ago. In Wadi Gharandal, we got some older ages between 120, 115 to 65,000 years ago. Interestingly, in this site in Wadi Gharandal, in site GH3, we have found interbedded Levallois flake. This Levallois flake was on the margin of the wetland, interbedded with wetland sediments, and we have done some or applied some different protocols using single grain feldspar and also quartz OSL. The ages were consistent into 84,000 years ago. So the time of the deposition of lakes was to 84,000 years ago, which means that the Levant was actually a well-watered that facilitated modern humans to disperse out of Africa through this region to Eurasia during the last interglaciation. We are talking about MIS5 100, again 129 to 71,000 years ago, which previously have been regarded as a failure dispersal. To proceed with our model, with our suggestion, we have integrated our data here with the human fossils in the Levant and Arabia, also paleo lakes and wetlands in Jordan, in Egypt, in Arabia as well, and the Mediterranean subtropics, which is considered as periods of enhanced precipitation at that time, and speleothem growth from south of Arabia caves like Hoti, Mukalla, Wadi Sanur, and Saka in Egypt, and Sorek Cave, which is one of the most important caves in the Levant, let's say, that records the speleothem growths like 200,000 years ago till now. We have a continuous record of speleothem growth at that time, and the Negev desert speleothems, and also the major and the most important record in the Levant is the Dead Sea record. And we found that, in fact, our data our ages, the timing of the human incubation 84,000 years ago, as revealed from Madi Garandal, Livalua Flake, is actually consistent with human periods in the Levant and also in Arabia, suggesting that the Levant was in a condition of enhanced precipitation and the climatic amelioration. The enhanced precipitation and the climatic amelioration at that time provided water resources to people to cross this region into Arabia and Eurasia to other parts of the world at that time. But we found something very interesting in our integration, that here are the records from Arabia, you know. We have nothing after 60 or 70,000 years to 20 or to 12,000 years, actually. So there is no records telling anything about, let's say, climate, environment, or archaeology in Arabia at that time. So what happened to the people of Arabia as they after MIS5? So we know that between 129 to 70,000 years ago, people exist in Arabia and here. But between 70 to the Holocene to 12,000 years, we have nothing, no records in Arabia. So that was another question that we are raising now to understand, let's say, what happened or how was the modern human or the human occupation patterns in Arabia during the glacial periods, because MIS5 is, as you know, is a humid period, interglacial period. So during glacial period, what happened? There are like three scenarios. The first one is that maybe the people of Arabia in the inland here just survived near some scattered oases or near the coastal environments, or maybe they have migrated or dispersed to another region. But what are the potential regions that they may disperse or migrated into, let's say? So based on this research, the previous work has been published in Science Advances actually last year in October. And this is like some new ideas I would love to share with you. So we have established a new model that the people of Arabia may have got back to the Levant during the last glaciation. We are talking about post 71,000 years ago. So for this purpose, we have also investigated the same sites and we obtained some new ages. Our new ages from Madi Hassa and Egregra says that we have the wetlands and the lakes in the Levant have been persisted even during the glacial periods when the world climate was dry, actually. So we got some new ages between 65 to 23,000 years in Wadi Hassa, and in Egregra between 56 to 33,000 years. Those ages, those records are not exist in Arabia, and this is a very interesting and a very big question, you know. So the 60,000 years ages is actually consistent with the genetic evidence, because the genetic evidence suggests that a major dispersal have been took place during 60 to 50,000 years ago, and it was somehow like short dispersal even. And also the 23,000 years, which is the high stance of Wadi Hassa, is consistent with the high stance of the Dead Sea. The Dead Sea is just nearby Wadi Hassa to the west. And the age of 19 plus minus 1 suggests the collapse of the dam. So there was like a natural occurring wetlands, those wetlands persistent because there was a dams, right? Natural dams. The dam has been collapsed like 20,000 years ago, and this This is the damming area here, and this site is after the damming area. We can see the dramatic change in the lithology to flash flood sediments, let's say. And also we have found in Wadi Hassa, for instance, some various types of flakes and the blades, microblades, were collected from site 3, site 2 and site 3, which is fit into middle and upper Paleolithic industry in the Levant. This may indicate that those lithics were, or those lithics indicate that a human existed actually or occupied in the Levant at that time. Again, we have made a new integration with the new data, with the new archaeological records in the Levant, and archaeological, paleoclimatological, and environmental records. And we found that this period between 70 to 20,000 years, actually, there are some evidence tells that this period was a human. So based on this, we suggest that the people of Arabia post 71,000 years ago have been migrated to or dispersed back to the Levant based, as you can see in this figure. So we have early dispersal into Arabia during the last interglaciation, and during the last glacier, we suggest that the people of Arabia got back to the Levant. So in general, the summary of our talk says that the Northern African route might be a potential route for human dispersal via Sinai Peninsula, and lakes and wetlands contributed and played an important role for the success of humans as they entered Asia. And humans may have occupied the Levant during the last glacial when Arabia witnessed dry conditions. Thank you very much.
Thank you, Dr. Abbas, for your presentation. Untuk selanjutnya, saya akan mengundang pertanyaan dari peserta. Bapak Ibu yang ada di ruang Zoom, jika ada pertanyaan bisa disampaikan di chat atau bertanya langsung. Juga Bapak Ibu yang ada di ruangan Episiono, jika ada pertanyaan. Ya, we have question on our chat room, Dr. Abbas, for you. Looking at the dating result at the sites in the Levant, can it be concluded that they were the ancestors of the Natufians?
Yes, the Natufians is actually a technology. We have Natufians, we have Ahmarians, you know, and the Natufians is, as far as I remember, maybe from 29 something thousand years ago. So yes, it might be from the Natufians, but it is Middle Paleolithic. We have the Middle Paleolithic artifacts, and we have ages that goes in the geology scale to the last glacial period, you know, between 70 to 20. And the first one, it is Middle Paleolithic from before the Natufians, from the Middle Paleolithic. But in our research, we of course we do some archaeology. We collaborate with archaeologists to identify the lithics that we are finding in our region. But we focus more into the time frame. You know, the age can tell us where we are, where we stand, and how to proceed in our research. So that's what we are actually focusing on. Again, the Natufians, the Ahmerians, there are several technologies based on the typology of lithic tools have been identified in the Levant, and it is quite complex actually. So, yeah.
Thank you for the answer. I hope it answered the question. Ya, ada pertanyaan. Iya, silakan Pak.
Thank you very much for Dr. Abbas and Mr. Dr. Hua clear and interesting presentations, but maybe I will ask in bahasa, ya. And, begini Mas, jadi pertanyaannya adalah terkait dengan gini, kalau dari riset-risetnya yang ada di Cina itu kan banyak menggunakan peralatan-peralatan modern dan canggih lah gitu ya. Nah, apakah di kita juga ada peralatan seperti itu sehingga kita bisa melakukan hal yang sama. Terus yang kedua, jika tidak punya peralatan yang secanggih mereka, apakah ada kolaborasi yang memungkinkan? Terus kemudian yang ini agak sedikit keluar dari sedikit topik, tetapi masih ada kolaborasi, ada kaitannya gitu. Ke depan gitu, ke depan Stephen Hawking almarhum itu pernah menyarankan bahwa kalau kita hanya mengandalkan bumi itu suatu saat akan tidak layak lagi dihuni lah gitu. Maka kita harus eksplor ke Mars misalkan gitu ya. Nah, apakah kan saat ini kita sedang mengeksplor Mars itu kan untuk di sana apakah ada kemungkinan oksigen, air gitu. Nah, apakah juga teknologi metode yang dipaparkan tadi bisa digunakan untuk juga melakukan riset terkait kondisi-kondisi yang ada di Mars gitu. Makasih.
Terima kasih Pak Sriono atas pertanyaannya. So, Dr. Abbas and Dr. Hua, I will try to translate the question. Oh yeah, only for Dr. Hua. Sorry about that. Yeah, so the first question is, on your presentation, you mentioned that you use a lot of very sophisticated, like the modern technology to dating. And do you think that Indonesia has those kind of technology in Indonesia? And if not, is it possible to do the collaborative research to work together?
Yeah. I think the machine is very accelerator. As I said, if you want to do the barrel dating, meaning that you have a experience of a long time of decay, so the level of concentration of the nuclide concentration is very low. So you need a high energy to date the samples, and by that means the machine is very expensive and very complicated. It's not archaeologist can do. No, you need some physicist or some engineer to run the machine. And so I thought it doesn't worth it to establish a lab of cosmogenic measurement, but you can establish a lab of pretreatment. So for instance, like me, we collaborate with the United States. So we pretreat we take samples, we pretreat the samples, and then we send to the United States for analysis. So it's more economy. Yeah. And also what we are doing here is like with Francois, with Sofwan, with Professor Halibidiando, we work on the Sangilan and some other sites. Yeah, we can collaborate with each other. So you have very great, you have very rich archaeological sites and in very good context, and we can cooperate and we can work together. I think it's a good opportunity, and this is how science works, right? Cooperation, right?
Yeah. And for the next question, quoting from Stephen Hawking that said that we cannot stay in Earth for a very long period of time. That is why now we conducted more research at Mars, like looking for oxygen, looking for water. So, is it possible to use your tools, to use your machine to find some kind of the what is it like the source of living in other planet like Mars?
Uh, this is a good question. Yeah, I think there's a potential because this method has been used to date the meteorite or tektites, and also in China we just launched how to say it, a satellite to the moon, and we take the soil from the moon, right? And actually, this method, the cosmogenic, can be used to analyze the soil in a luna in the moon, and it can tell us the surface erosion or activity, how fast it eroded. Because normally we think the moon is kind of stable, right? The surface. But by using this method, you can know how long the soil can be exposed on the surface of different planets. The moon, maybe the Mars, or maybe in the future, different planets. Yeah, I think the method is it can be used in different backgrounds, but we need the samples. Yeah, thank you.
Yeah, thank you for your answer. We have another question from the chat room at Zoom. It's come from Taufik. Taufik's come from, mohon maaf Pak Taufik kalau saya salah membahasa Inggriskannya, Balai Pelestarian Kebudayaan Wilayah 5. He comes from Culture Preservation Office, Region 5 at Jambi, who has a huge Buddhist temple in Sumatra. So in this case, he said that he found a brick with, it's not a completely burned brick.
Correct, yeah.
Brick, yeah, brick, the brick, yeah. He said that it has the carbon in the middle of the brick. So he just want to ask the suggestion from both of you, which methods can be used better to dating those bricks.
Yeah, for the bricks, and as we know that when the bricks are made, they are subjected to some heat, right? So thermoluminescence could be applied on this materials actually, and maybe if he found some charcoal or I don't know organic material, something that can be dated in that site or from the break by radiocarbon, he can apply both. Actually, if you can apply both, you will get like a solid age that you can compare with each other. But in a luminescence point of view, thermoluminescence for bricks is more suitable because those materials again it provide us a data about the last heat. So luminescence give us the last exposure to the sun. Here the last heat. So thermoluminescence could be applied on this materials. Yeah.
Thank you,
No,
Dr.
you
Abbas.
can reply.
No, I replied to one and it was not me actually who replied.
Semoga itu menjawab pertanyaannya untuk Pak Taufik. Apa ada pertanyaan lain dari ruangan RP Suyono atau dari ruang Zoom? Oh, ya.
Okay, let me introduce myself. My name is Aulia Arifin Billah. I'm from radioisotope and radiopharmaceutical technology research. Okay. Yeah, I want to ask about the luminescent techniques where you use mineral feldspar and quartz to find out the last time this material was exposed to sunlight, right? So that you can know the limit of the energy stored in it. Uh, so the what about the radioactive material? Will it not affect the measurement? And what the radioactive rays can affect the stored energy? Okay. So this why I asked to you because I am interested in nuclear battery.
Yeah.
Okay.
Yeah, thank you for
Yeah.
your question. Actually, the radioactive, we talked that the age has two influences. The first is the DE, the equivalent dose, which is, let's say, the sum of energy has been stored. So we are stimulate this energy, right? By subjecting like blue, red, infrared light in the machine, in the lab. Okay. So this is for the equivalent dose. Uh, f- what are the value dose? What you are asking about actually is the dose rate, because when the sediments are, let's say, buried, okay, so we have this layer. In this layer, the sediments have been buried, and then another layer deposited, another layer deposited, another layer deposited, right? So this here and here and here, wherever you want to date, if you want to date this layer or this layer, okay, there are some cosmic rays that goes from the sunlight, from the dead light, goes from here, penetrating into the sediments, influence on the sediments, right? Like alpha, beta, and gamma. For alpha and beta, they are like it. We must be like very, very precise with that, like to collect the dose rate sample from nearly the same place where we got the sample. Gamma can be similar or homogeneous with the range of 30 centimeters of the meters around the sample. So the sample got and the radioactive, let's say, are attenuated with depth, right? So when the sample is on the top, it will receive like more radioactive. When it's like at lower depth, it will receive like lower and lower because of the attenuation. In case of cosmogenic nuclide, we don't prefer to sample from uh, 5 or 6 meters of the section, because of this actually reason. But for the luminescence dating is okay. We can date even from 30 centimeters from the top of the section if the materials are okay, I mean, if they are not reworked materials. So yeah, this is where it came from. Okay.
Okay. Thank you.
Yeah, thank you very much.
Selanjutnya kita ada penanya dari ruang Zoom kepada Ibu Marina Frederick. Kami persilakan.
Ya. Baik, terima kasih Pak Niko. Ya. Thank you, Pak Niko. All right. First, I'd like to thank for Dr. Hua and Abbas for the very interesting presentation. I'm a marine geophysicist, so I'm new on this dating of sediments and stuff. So just bear with me with my basic question. As a marine geophysicist, we have some samples from the ocean, a core sample. So it's not that big, right? They are from shallow ocean and then deep ocean. So we have those, but many of them are not deeper than 10 meters from the seafloor. I'd like to know from either one of you can answer me. how much samples do you need for dating, and also how long would that take? Thank you. For example, we have some volcanic ash layer.
Okay, so what is the estimated age of your samples? You are talking about the late Pleistocene or early Pleistocene? Do you have an idea about this?
I have no idea.
Okay, so
We just took a sample first. Yeah.
yeah, so maybe first of all you can try luminescence dating, because luminescence dating it works for like 200,000-300,000 years, and it just need very fine quartz like older than 63 muon. It's okay. So fine grains works for luminescence dating.
Mm.
And if it's out of the range of luminescence dating, then you need to try maybe cosmogenic. And but the problem is that you may not have the core very big, large grains. Normally, we need grains as large as 100 micron, which is 0.1 millimeters. So normally in ocean, you don't have this material.
Yeah, we do.
Yeah, so
Very
maybe
fine. Yeah.
yeah, maybe the best choice is luminescence dating.
Okay. And even though it's not buried deeper than 10 meters?
No, luminescence dating doesn't require the depth. As long as it's buried in maybe 10 centimeters, it's okay. And also you have the water to share the light. Yeah. Right? Do you have that?
Okay. Okay, great. Thank you.
And you asked about the size, maybe, right? Of the sample, like how many sample we
Yeah,
need.
how many is it needed for
In fact, for luminescence dating, we don't need that much. It depends, like, because we will, as I said, that cores and feldspar exist, are naturally occurring, and they are exist in all sediments. Let's say at the end, we may need like 50 grams, maybe less, maybe 10 grams. I don't know to do all the protocols in the of course or feldspar in the in the lab. So for me, I use like a 20 centimeter length tube to insert in the layer and to get the sample again. So it is something like 300 grams is okay. Yeah, and in the sediment part, yeah, 300 grams is okay. I think yeah, something.
Be exposed to light.
Yeah, and should not be exposed to light. This is,
Oh,
the
not exposed to light.
If the sediments are exposed to the sunlight after you take it from the car, so the edge will be today.
Oh, okay. So
Yeah.
we use cores that are transparent. So obviously the edges will be exposed.
Yeah.
Okay.
But,
Right.
but the outer part is exposed. We can remove the outer part,
Inner
okay,
part, okay.
and take the inner of the core, Yeah.
All right.
Yeah.
Okay. Thank you very much,
Thank you
both
for
of you.
Terima kasih untuk pertanyaan dan jawabannya. Apa ada pertanyaan lagi dari ruang RPSiono? Dari ruang Zoom mungkin? Ya, silakan.
Okay, thank you very much. A lovely presentation. And I just want to ask two questions. First one is about the luminance dating. For the case of thermoluminescence dating, do we have also take like pair sample for annual dust for in the surrounding of our sample, our primary sample, or not? For the case of thermoluminescence for the luminance dating. And the second one, do you the first one is when we take a sample for the means of making thermoluminescence dating, do we have also take the like a sample, another secondary sample in the surrounding the matrix, for example, in the surrounding our primary sample, to just to have an idea about the annual dose or the today dose or something like that. And for that, and because for the optical stimulated, we should, right, doing that. And then for the second one is for the Homo sapiens in the Middle East. Do you have also like a more robust type of general environment occurred during the time of early modern humans occupants, early modern human habitation in the Levant? Because here in Indonesia, like we say, like we have two, for instance, for the early occurrence of Homo sapiens in Indonesia. The first one is from Sumatra. They were found in the assemblage of really green rainforest environment about 70,000 years ago. You already show it. And then also in Punung, the occurrence, the arrival of Homo sapiens, that more or less maybe you remember the Songtrus period, the layer just after approaching the end of the Emian interglacial. It's a humid period, and the biostratigraphy and the biogeography and the faunal assemblage of our unit, it's suggests that it was a really humid environment. So we have two locality in Indonesia suggests that 100% Homo sapiens related to the humid and tropical rainforest environment, the evergreen rainforest environment. How about in the Middle East? Do you have any like preferable reconstruction about early modern human? And the second one, it also compared. Can you give us also the example of what type of environment before the arrival of the Homo sapiens in the Middle East or in the Levant, like you say? Thank you.
Thank you very much. Some information. For the first question about the thermal luminescence, it is always good to collect like more samples, okay, from the same site. And I don't know, I can't imagine that if you like you have your main sample, right? Don't be very far away for the backup samples from the same sample, because it is heating and the heat might be heterogeneous, the influence of the heat in the sample where you are collecting. And also you have to collect samples for the dosimetry. Okay, so this is for the first question. The second question, in the Levant and in Arabia, we have evidence for the human incubation during, you call it the Emian, which is MIS5E, right? We have evidence for human incubation and the early one in Mycelia cave. Actually, they lived in caves, basically. Okay, so when you look at the geology of the Middle East and of the Levant, particularly the Tethys, transgression and regression, deposited a lot of limestone. So we have so many karstic caves in the Levant. For the modern human skulls, we have like Mycelia cave, Kafzi cave, and skull caves, right? In north of Palestine in the Jalili area, and it is actually near the Mediterranean Sea. Those caves are karstic caves again, and the humans like occupied those caves in that part. between 200,000 years ago, 130 to 90,000 years ago. We go to Arabia, where recently they found the finger bone. The finger bone was found and associated with lake sediments. And the footprints 115,000 years ago is actually in a lake sediments. Okay. Again, let's go to the south of the Levant. I just want to give you like some kind of overview. In the south of the Levant, there are archaeological tools in the rock shelters and in caves. The south of the Levant, which is the south of Jordan, north of Arabia, let's say, it is desert, right? So we have rock shelters like Tar Faraj, Tar Fawaz, dated to somehow like 50, let's say 50, 49 to 37,000 years. So this also supports a human incubation. So what we have caves, we have lakes, and we have shelters. For the lakes and wetlands in the Levant and Arabia actually indicate that a savanna type occupied or environment occupied that area at that time during MIS5E precisely. Okay. There are evidence again of some herbivores and carnivores were found in Arabia. These herbivores and carnivores, the carnivores, they eat each other, the herbivores, they eat like more grass, right? So they need resources. So there was like conditions that make them, occupy that part of the world at that time. Yes. And again, maybe here you have like tropical environment, right? And yeah, it doesn't. Yeah, always. I mean, the behavior, like we adapt, right? So you are living in a tropical environment, right? I'm living in a Mediterranean climate zone. In the south of Jordan, in my country, they are living in the desert. So we have the ability to adapt, right? With the environment. Yeah. People are living in the Tibet plateau as well. Yeah. Yeah. Thank you.
Thank you very much.
Okay, we are almost in the end of our sharing session today. So thank you for the delightful discussion. Now I would like to invite Dr. Sofwan Nurwidi as our director to have a closing statement. Pak Sofwan. Oh iya, mohon maaf saya baru mendapatkan informasi bahwa Pak Sofwan sedang monef, jadi berhalangan untuk memberikan closing statement. Mungkin ada sedikit hal yang ingin saya sampaikan. So to sum up, as Dr. Heri Yogaswara mentioned in the very beginning of our sharing session today, he said that dating is extremely important in archaeology because we can consider dating as a core in our discipline, but still we need to adopt from another discipline. And I take a note here that as an archaeologist or as a human being in general, we always curious about two things. First, where do we come from? And the second is, when does it happen? I believe what has been presented by Dr. Hua and Dr. Abbas this morning can give us an alternative method in dating and also to give us a better understanding to answer those questions. Thank you. Thank you again for your presentation, Dr. Hua, Dr. Abbas. And thank you for all participants for the great discussion. See you again in the next sharing session from Research Center for Archaeometry. Thank you. Syukron and syesye. Mau foto bersama bagaimana panitia? Atau ya, kepada Bapak Ibu yang berada di ruang Zoom, mohon mengaktifkan kamera. Kami akan melakukan sesi foto bersama.